So glad to be doing the science webinar today. As Lisa said, I'm the Chief Scientist of the Marine Debris Program, in case there are some of you I haven't met. This talk might be a little bit different than what we're used to in the webinars. I've given it a number of times at different international venues, like the 7th International Marine Debris Conference. But I'm happy to deliver it here, or a version of it internally, because I think it provides a nice refresher for those of us who are practicing scientists, and also will provide some insight for our non-research oriented staff as to what is required to achieve scientific rigor in a study or in an experiment. And so I'm going to start out with what are some of the key principles of field experimental design that are oftentimes not considered when ecological monitoring programs are being developed, including for marine debris sometimes. And then I'm going to follow up with a discussion of how our program has engaged in many different iterations of our own shoreline monitoring project to incorporate these principles and make our monitoring project more scientifically robust. So first, I want to acknowledge Hillary Burgess, who is our program's monitoring coordinator. I see she joined the webinar because she is a co-author on this talk, whenever I give it and wherever I give it. Okay, and now I'm in read view, but can't get my slides to advance. There we go. Cool. So the first thing we need to do is ask ourselves, what is monitoring? What is it and what is it not? Because oftentimes this term gets tossed around to describe activities that really are not monitoring at all. So the first bullet is what monitoring is not. It's not selecting sites haphazardly that are sampled irregularly, and during which time some variable gets measured. This sort of activity falls under what would be like a simple status report. What's there? We went out, we measured things, here's what was there. But there's no real intent to estimate a change or the condition of the variables that you're measuring. But what monitoring is, what true monitoring is the systematic measurement of variables and processes that includes repeated measurements over time using the same methods in the same place. And the important thing is that there's actually a specific reason for why you're collecting that data. So what is the reason for monitoring? So as I mentioned, we're going to go back to some of the first principles of experimental design. And the most critical component of any experimental design is first asking yourself, what is the question to which these data are the answer? So conservation biologists have published at length on this, on what makes monitoring programs successful or unsuccessful. And you can just see from some of these quotes that the single most important driver that pops out, single important driver of success in monitoring programs, is development of a clear, purposeful question that the monitoring data will successfully answer. And failing to explicitly state what the goals of the monitoring are, or what you'd like to learn from a monitoring program, is a primary weakness in most ecological monitoring programs. And the reason being is that the question you're asking and how you frame that question is going to dictate all aspects of how you actually sample in the field. And so that's what we're going to work through next. So what are the questions you could ask for monitoring? So I really like the two papers I cited at the bottom of this slide, and I'm happy for people to take screenshots or whatever you need to do if there's some information you want to capture. So these authors define and discuss various types of monitoring that are based on some specific goals or questions that monitoring could ask. And throughout the rest of the talk, when I'm talking about general principles, I'm using marine debris, shoreline monitoring as kind of the example, and debris loads as the variable of interest in these descriptions. So here are some of the questions you might ask from monitoring. The rest of my talk is really going to focus on the first two. So oftentimes when it comes to marine debris on shorelines, we want to know, what are the drivers influencing the distribution and abundance of debris on shorelines? And then oftentimes we want to know, well, over time, are we seeing a change in debris condition? Is it going up? Is it going down? Is it staying the same? Because perhaps If there is a change, especially if it's going up, then there might need to be some management intervention that we need to think about. And the three other types of monitoring are really about the management interventions themselves, asking questions about, okay, we want to implement this management intervention. Was it implemented as we prescribed it to be? Was the management intervention effective in reaching the goals that we stated? Or were there unintended consequences of this particular intervention? So those are some of the questions that you could ask of a monitoring program. And like I said, moving forward in this talk, we're really thinking about process and drivers, or more specifically, the second one, surveillance monitoring, and asking whether debris condition is changing over time. So once you've clearly articulated what the question is, then you have to define what is called the scale of inference of your monitoring program. And I'm not going to try to geek out too much in this talk, but sometimes I do have to talk about some scientific principles, and I'll try to do my best to explain them more generally. So what the scale of inference is this is the extent and the resolution over which your samples must be taken. Importantly, your ability to generalize about your monitoring data is going to be limited to this scale of inference that you choose. So your data can't really talk about things that go beyond the scale that you've designed your experiment to address. And what's important to remember is that there's no right or wrong scale, because the scale is dictated by your question. So it's very specific to how the question's framed. So I just mentioned scale of inference, and it has these two dimensions, which are called extent and resolution. So what are they? Extent is the overall size of your study area, or in this case, the overall size of your monitoring area. And resolution deals with the size of the individual units of observation, or the sample units, if you will. And both of these dimensions of scale must be considered at three different levels. You've got spatial, temporal, and ecological. So the spatial extent pretty much just means what are the geographic dimensions over which you're going to conduct your sampling or your monitoring. So these could be global, national, regional, it could be on the local level. Your temporal extent is then the period of time over which the sampling is to be conducted in more of the long term. So if you're thinking about debris change on shorelines and we want to talk about trend, are we thinking about decades? Are we thinking about something that's happening annually or something that's happening monthly? And then we have the ecological extent, which sometimes is a bit confusing, but this is going to be the population or the assemblage that is of interest to you. In our case, it's marine debris on shorelines. So the assemblage we're interested in is basically all debris items for which the sampling is going to be conducted. And then your resolution kind of fine tunes those parameters. So if you think about spatial resolution, that's the actual dimensions or size of the sampling unit that you're looking at. So you might be monitoring an entire length of shoreline. You might be just looking at a transect. You might just be looking at a plot. Your temporal resolution is how often you do your sampling. So it's not really the long-term looking at trend, but it's how often do we have to go back and take samples at these particular sample units. And then the ecological resolution is also refining that assemblage of interest. So refining the type of debris that we're interested in. And so you're going to set probably particular criteria. So it might be specific size classes or specific material types. So the next step, once you've defined what your scale of inference is going to be for your monitoring program, you need to determine the level of change in your data that you want to be able to detect. Remember, for this exercise, we're thinking about changes in debris on shorelines over time. So we have to think about, well, what's the level of change that we feel might be important to a policymaker, or might be for our own interest, or just generally, it could just even be what's an accepted level of change that people just typically do for marine debris. So this is important because the level of change you wish to be able to detect will dictate the location of your sample sites, the number of samples that need to be taken, the frequency of sampling, and the duration of sampling. So that's really important. And the way that you can figure that all out is using statistical methods that are designed specifically for these purposes. Not surprising, these particular methods are really challenging and often exceed the capabilities of most practitioners who are actually going to perform the monitoring. This includes our staff in the Marine Debris Program. We are not super strong statisticians in the sense of large-scale survey design. And so having to do this really highlights the importance of cultivating collaborations, not just among other researchers and managers who are interested in the information, but also thinking about survey statisticians who can help you figure out what this design should look like for your monitoring program based on the question that you're asking. And we're going to dive into that a little bit deeper later. But all the while, we need to remember that monitoring, no matter what you're monitoring for, is an iterative process. And that once you have some data in hand, it's always really good to have a look at that data and see if there's any necessary adjustments or refinements that can be made to the way that you're collecting the data. And so analyzing and adapting are really important when it comes to monitoring. And you're going to see those themes creep up through the rest of the talk and be kind of the focus as I walk through our program's shoreline monitoring project and talk about some of the adaptations and refinements we have made over the years, always going back to these first principles of experimental design. So if you're not aware of our marine debris monitoring and assessment project, this started back in 2009 when the program began developing an on-site data collection method for shoreline debris. And at the time, the goal was simply to compare debris loads between different land use types. And so the method was really limited to estimating debris load at the level of an individual site. It wasn't meant to be scaled up. And this method was largely modeled after some European protocols that were in use at the time. Then in 2011, we had the Japan tsunami occur, which a lot of you are familiar with the aftermath of that. But then there was collective interest across the west coast of North America in particular to rapidly collect data on debris loads on shorelines in anticipation of having an influx of debris from this natural disaster. And so our program quickly published a guideline for how to perform this on-site data collection method based on what we had already been working on and shared this with interested parties. We also launched a publicly accessible online database where all the data is housed. And we provided what we called a toolbox, which contains some training materials and data analysis tools for how people could get started using this data collection method. Won't get into a lot of details about what happens when you go to a monitoring site, but in a nutshell, like many other existing shoreline marine debris data collection methods, it involves designating a specified length of shoreline for sampling. In our case, it's 100 meters, which you can see here in this little figure. And then within those 100 meters length of shoreline, you've got 4 random replicate transects that you're going to sample that represent subsamples because they get averaged together. And then so a person or persons walk the transect and look for debris items in certain material type classes that are greater than or equal to 2.5 centimeters in size. So as word got out about this particular protocol, other people and other entities became interested in using our method. And after a few years, the project really evolved into a participatory science initiative, wherein we're providing partners with the tools, not physical tools, but like the training materials I just mentioned, giving them the tools they need to collect the shoreline debris data at their own self-selected sites in order to answer their own questions that they might have about debris loads in their area. And all of this in the hopes that they will use that information to guide management interventions and also raise awareness overall about the issue. And in fact, people have used our shoreline monitoring protocols for these purposes. I won't get into details about those, but you can have a look on our website, which I'll give you the link to at the end for the monitoring specific portion of our website. So as the project is tootling along and we're getting a lot of interest and it's really become about participatory science, we did receive a fair amount of feedback from partners using the method, particularly on the training materials and the database itself. So beginning in 2016, we embarked on a rather detailed evaluation of the project thus far, from both a scientific and a stakeholder perspective. And so we did this through interviews with participants and data users. We performed an analysis of the entire data set as a whole to identify its limitations, and we performed an evaluation of the on-site protocol itself to help resolve some sources of bias in the data collection that had been identified when we did the full-on data assessment. And so those efforts resulted in recommendations for ways that the project could better meet partner goals. And the last couple of years, we've focused on bringing all of these insights and lessons learned together into updates that included a new survey guide, online training videos, educator resources, and a complete overhaul of the database to include data visualizations, which is really exciting. So it was really a true rebooting of the monitoring and assessment project. The good thing is that because the data collection method is standardized, individual surveys can be combined and compared so that they can be used to understand the state of marine debris. However, this particular method was not intended to allow for these individual sites and the data collected at individual sites to be representative of a larger or a greater extent. Because partners are self-selecting sites and they're collecting data at varying timescales, there's a lot of spatial bias in the data, and the temporal and spatial coverage of the data is limited. So the scale of inference is very, very localized. And so very recently, we embarked on a very ambitious journey to kind of resolve this limitation and figuring out how can we actually scale up spatially and temporally such that we can use our on-site data collection, but put it to use in a systematic way with repeated measurements over space and time to paint a picture of debris status and trend on shorelines of the United States. So truly implementing a shoreline marine debris monitoring program. And to do this, because it requires some very complicated statistics, as I mentioned previously, we partnered with Western Ecosystems Technology, which is an environmental statistics consulting firm that specializes in large-scale environmental monitoring designs. And they were just awesome. We learned, Hillary and I, a great deal from this group. So the remainder of my talk is going to focus on this journey of how we took this on-site data collection protocol and have now come up with a grand scale survey design across shorelines of the United States, including the Great Lakes. And I'm constantly going to be linking back to those basic principles of experimental design that I introduced at the very beginning. So hopefully those will look familiar to you. So as we have already learned, hopefully, the most important thing to do is figure out what your question is. So we actually identified 2 questions that represented both short-term and long-term monitoring goals that we wanted to ask on a regional scale. So you can see we've got the US divided into 10 regions. You can see in the figure at the bottom of the slide. And so what we would like to know is that in a given year or in 1 year's time, what is the status of shoreline debris in each of these 10 regions? And then at a larger temporal scale, how is the debris load in that region on their shoreline changing over time? Not only year to year, but also looking in the long term maybe in a decade's time, how has that debris load changed? Sorry about that. So we have two specific questions there. And so the next step, man, I should have made this live action. Like I should ask you guys, what's the next step? But the next step is setting the scale of inference. So here's this crazy table again. And so we're going to start with the levels of extent, which is about the overall size you want your monitoring program to encompass. So I already just mentioned in the previous slide, we wanted to look at debris at the scale of regions. And you saw the little map of the 10 regions. And these were designated according to a previous shoreline monitoring effort here in the US that took place back in the late 90s and the early 2000s. And I'm going to mention it again later, but these regional designations were largely focused on prevailing coastal currents and evaluations of what are the geographic boundaries, if you will, of different types of marine debris. So were there types of marine debris that appeared more frequently in certain locations around the United States? And also a bit of the designations revolved around logistics, to be honest. So all this to say, our spatial extent for the purposes of designing a national level survey is regional. And then what is our temporal extent? Well, I also just mentioned in the previous slide that we had two extents. We wanted to be able to survey for a year and get a good, solid, precise estimate of just the status of debris abundance on shorelines. But then we wanted to figure out a multi-year effort and what that might look like in terms of getting a handle on how these debris abundances are changing over time. And then for our ecological extent, we are interested in all debris items, but particularly those that are found on sandy pebble shorelines and shorelines that are publicly accessible. So we had to put some limits on what that extent could be, just to facilitate the ability to actually carry this out. Now we've got our dimension of resolution, which is more fine scale. So these again are the size of the sample units. What we've learned from doing the actual on-site protocol that I talked about before, our spatial resolution is 100 meters of shoreline. So we take replicate transects within that 100 meters and use them to tell us what is happening in that 100 meters of shoreline. I mentioned that for the MDMAP on-site protocol, our temporal resolution is monthly. However, we weren't certain that when we scaled this effort up, that we would still have to sample monthly. So that's why there's a question mark there. We went in with this anticipating that it would be, but we weren't entirely sure. And then lastly, again, ecological resolution. So we're fine-tuning even more this assemblage of debris that we're interested in. And so we're interested in not just the sandy pebble shorelines that are publicly accessible, but specific debris items that are greater than or equal to 2.5 centimeters in size within 7 different material types. In terms of our desired level of change, so this is the next step in the experimental or survey design process, well, we wanted to be able in 1 year to have a reasonably precise status estimate. And then we decided that in the long term, we wanted to be able to detect changes in debris that were either greater than or equal to 20%, because we felt that that is a large enough percentage, you're probably actually going to be able to see a change. But also in previous efforts that have tried to do this, it kind of seems to be the number that people use. And that's okay, because you'll see later on that we kind of played around with that number to see if it was actually feasible. So again, here's the part where I would ask, what comes next, folks? Now that we've described or defined our desired level of change, well, now we need to know, okay, great. How many sites do we have to go to? How often do we have to go to those sites? And how long, what is the duration of this long-term sampling in order to be able to detect this level of change in debris on shorelines in the US? So to do this, we performed, I should say Wes performed with our input, a power analysis. Unfortunately, it's really well beyond the scope of this presentation to give a primer on power analysis, but it's an intensive, iterative calculation, and you use it to estimate the smallest sample size that you need to determine if the result of your particular model or statistical test is due to chance, or if it's a true result and if it's significant. So in our case, it's going to help us determine that if we see a change in debris load over time that is greater than or equal to 20%, is this a true change in the debris load, and is it statistically significant, or is it just simply due to chance? What's super ironic about power analysis is that you actually need data to do the power analysis. So it's a bit of like chicken and egg. You need to have some data about your population of interest, in this case, marine debris, to perform a power analysis. But in our case, we were really fortunate, as I mentioned, to have access to a large shoreline debris data set that was collected in the late 90s and early 2000s as part of the National Marine Debris Monitoring Program, which was sponsored by EPA, and the monitoring was performed by the Ocean Conservancy, using the same regions that we intend to use, except they did not include the Great Lakes. And they used a somewhat similar data collection method on site. And they looked at the different regions over the course of 5 years at a minimum. Some regions had more than 5 years worth of data. So in very, very simple terms, because I could probably never explain this in a technical sense, but we took this data set and we ran it through a model to determine what the trend in marine debris loads was across each region, across the whole data set over those 5 or more years. And in addition, the model told us what the associated estimates of debris abundance were in each region over those years. And the model also gave us estimates of the components of variance of the data. What variance is basically how do the debris loads vary across different years, across regions, across sites? How do the debris loads vary within a site of a given year, and so on? And so the model tells you what are the proportions of those variances. So like which one is more important relative to the others in a way. So knowing that for a real data set, we take that information and we can simulate many, 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 many other data sets that have the same basic structure as the real data. And then we can model those simulated data sets and force them to exhibit the change over time that we are interested in. In this case, we were really interested in 20% change. What you can also do with the model is then systematically manipulate sample size, sampling frequency, sampling duration. You can manipulate those parameters in the model and see what happens in terms of our ability to detect that level of change that we have forced the data to have. So it's an iterative process of evaluating the trade-offs among all these various combinations. And there were a lot of them, and it takes a really long time. But for the purposes of this exercise, we're just going to cut to the chase and tell you what we found out from this power analysis. So in the end, it was recommended that we should survey 62 sites in each of our 10 regions, and that this sampling should consist of a panel of 12 sites that are visited every year. And within that year, you're sampling these 12 sites repeatedly on a quarterly basis. And then you need to have a second panel that has 50 sites that you just visit once every 5 years. So you're not replicating the sampling within a particular year. And so this particular design provided a sufficient test size and sufficient power that we could reliably estimate debris status in a given region using 1 year's worth of data. And we could reliably estimate a change in debris loads over time if we carried out the entire monitoring program for 11 years. So let me skip back to the second bullet, test size, test power. These are the statistics that come out that tell you basically what is the acceptable level of error that you're willing to accept when you're looking at this change over time. And so in terms of test size, the 0.15 probability, this means we have a 15% chance of concluding that the change we detect in debris load is true when it's not. So basically, oops, we made a mistake. So we've got a 15% chance of saying, oh, we noticed a change of 20% or more, but it might not be correct. This level of 0.15 is a pretty standard level that people use when they're thinking about test size. The test power, what that tells you is that, but we have an 80% chance of concluding that the change in debris that we observe is indeed a true and significant change, and it's not just due to chance. So those are some pretty standard statistics that are used in power analysis, and these are pretty standard values that people strive for when they're designing experiments or field studies or long-term monitoring. I did it again. So we got the read to visit design. That was great. So the next thing we had to do is figure out, okay, well, where do we sample? We know how many sites and the temporal revisit of all these sites, but where are we going to go do this? So not surprisingly, this involved another really in-depth process. The first thing we had to do was figure out what is going to be the sampling frame, or basically what's the set of all possible sites that could be sampled. And so this involved getting a linear shapefile of land use and land cover along the US mainland, barrier islands, and bay shorelines in each of the 10 regions, and refining that shapefile a little bit, but then using this sampling procedure, which is called a generalized random tessellation stratified sampling. Try saying that 3 times real fast. So basically, this is a spatially balanced method of selecting sites to survey. When you have a spatially balanced design, it reduces the frequency of putting points close together, which is really important. So it ensures that the points that you're going to sample are geographically diverse. As a result, there's less spatial correlation across sampling units, which is really important from a statistical perspective. And this kind of design also allows for you to oversample to accommodate any issues that might occur when you're trying to do surveys in the field. Like maybe you go out to a designated site and you can't do it, you can't access it for whatever reason. And so the statistician gave us 5,000 sites per region that we actually worked through, not all of them, but we worked through until we got 80 sites that we felt were suitable for sampling. And so that's our master list of where we should go. And this is my last slide. So what are the next steps? Well, the next steps are hopefully to just do it. So we are waiting for a contract solicitation to hit the street any day now through ProTech. And this awardee will take the lead with our guidance on implementing the spatially balanced design that I just discussed. We're hoping to have the contract in place by the end of this summer. And at the moment, thanks to the bipartisan infrastructure law, we do have the funding to conduct the first year of sampling to get us those reliable status estimates in each region. And we're trying to remain hopeful that we will be able to find the funding or support to realize the full design of the monitoring program, which would require 11 years of sampling. So with that, I'll stop. And if there's any questions or however we want to proceed next.